Okay. Last time we discussed the topic on dynamic analysis of SMIB system, and we had basically discussion on how to model the SMIB system. And if you remember, we started with the classical model, and then I discussed in brief about this example from the Kundur book. And then, in fact, I discussed how to develop the equations and then perform some analysis. So the equation development in terms of including the field circuit, and then the complete model with the excitation and AVR in the SMIB. And then I was discussing about the stable. So in fact, I'm not sure, because with the last discussion, it was not clear, because Ibrahim, you had some queries, right? If you remember.
About what?
About how do we get this synchronizing torque coefficient, and then the net synchronizing torque coefficient and the damping torque coefficient, right?
Yeah, I did not understand that very well.
Yeah. So in fact, I modified some of my PPT, because it's through PPTs only I can teach here. So I modified, and then maybe I can discuss a little bit on those equations which I have not included in my previous lecture last time, I mean. So I modified some of the PPTs, and then I will upload it on the canvas. I will do that. So with that, let me we will start from here, in fact, because that is the basic point which is about the rotor angle. So this is the synchronous generator representation. The stator part here, we have the 3 stator winding on the stator. Then this is the silent shape field circuit, or the rotor, or silent shape rotor of the synchronous generator, which will be excited from an external source, and you get a sinusoidal signal from the 3 stator terminals here. And the 3 stator windings, they are 120-degree space displaced with each other. Now with this representation, if I consider the phase axis of phase A winding, so let's say this is 1A and A prime. So the current enters and the current leaves here for the phase A, right? Then its axis, the axis of the phase A, it is this way here. So this is the coil representation for the coil which belongs to the phase A. So it is along this axis. Let's say the rotor position is this way. It is anti-clockwise rotation. So this is the rotor position. And then since it is a silent shape rotor, so you have a concentrated field winding along this axis here. So the orientation of the main field, or you can say the concentration of the main field, it is the axis which we call it as D axis, direct axis. So this is actually the field axis here, and that is represented by field MMF here. Then the axis 90-degree to this is known as quadrature axis here. So this is Q axis. Now in this axis, when you have the orientation, then you don't have any flux linkage here. It is 0 basically. So thus the one is the field axis, the main field axis. This is also the D axis, and the 90-degree to this D axis is your quadrature axis here. And now when we have the current flow, because let's say you load the stator terminal here. So when you have a current flow, then there will be a phase current flow, let's say in the phase A winding, yeah, right? And because of that, because of the current flow in this phase, its orientation of MMF vector. So that we call it as armature reaction MMF. Because of phase current A, that is phase A, it will be oriented along this axis. So what you find it here, so if you decompose, this is the D axis, this one, this is your Q axis here, which is along parallel to this axis, and then this is the placement or the orientation of armature reaction MMF. So one is the field MMF, another is the armature reaction MMF here. With this, we consider, let us take this diagram. So what you have it here, I have shown, because let us consider more uniform distribution of the flux in the air gap here. So that's why it is shown as for cylindrical shape rotor, but it doesn't matter. So you have the two phase axis for the coil here, and then this along this axis, along the coil axis, you have the armature reaction MMF here place. This is the axis, this is the field axis here, which is oriented along the main field here, that is. Then in parallel to this armature reaction MMF, we have drawn this vector here. So this one. So because of the current flow, in the phase winding here, you have an armature reaction MMF, and this armature reaction MMF is actually 90° to field MMF here, main field MMF. And because of that, you have a resultant MMF. So thus, the resultant MMF here is actually the phasor sum of field MMF plus armature reaction MMF. And with this direction of rotation, anti-clockwise direction of rotation, what you find, the resultant MMF, this is the resultant MMF, lags behind the field MMF here. And that is the basically the rotor angle delta. So that is the you can say the originality of the load angle or the power angle or the rotor angle here. So it is basically the angular separation between the main field MMF and the resultant MMF here. More clear way it is shown here, in fact, because this is the field MMF and this is armature reaction MMF here, and this is your resultant MMF. Now, if you look at what we have shown, the current flow in the phase A winding, it is along the phase A axis, and again the EMF is also induced along the phase here, stator terminal. So what does this mean when I show the vector of current in phase with voltage? What does this mean? Yes, please. When I show the current flow in the stator winding, it is in phase with the voltage. What does this mean?
If the current is in phase with the voltage?
Yeah, but what does this mean?
Your load is resistive, you don't have any reactance.
Okay.
Right?
That means the power factor is unity. Right?
Yes.
The power factor is unity.
Factor is unity, yeah.
And yes, that's fine. And then if this magnitude will depend upon what is the loading on the generator. What is the magnitude of this here, right? If there is no current flow, if there is no generator loading, right? If there is no generator loading, this will be absent. And in that case, the resultant and the field MMF both will coincide. So this angle delta exists only when you load the generator. So only when you have the current drawn from the generator terminal, then only you have this current and thereby this MMF. And because of this MMF, this resultant MMF will exist, and that means because this is the resultant of main field and the armature reaction MMF. And higher the loading, let's say you have increased the current, you have increased loading on the generator, so this MMF will increase, and thereby what will happen, the angle delta will be more. The angle delta will be this one, because this will be the MMF here. Armature reaction MMF will increase, and thereby the angle delta will increase, because this will be now your resultant MMF. This is one case when I say the current is in phase, but it could be a saying like the current lags here. This is the current lagging behind the voltage. Then what will happen? This MMF, what we have it will be basically in phase with this. It will be in parallel with this one, and as a result, the resultant MMF is further change. So that means even for the same magnitude of current, if you have the lagging power factor, the resultant MMF will be with more angle here. So this is how the rotor angle delta changes with the magnitude of the current and as well as the power factor of the load here, right? And thus, in fact, what is shown here, if I remove this, and if you look at, just say, this is the main field MMF, and the EMF which is induced because of the main field, it is 90-degree, right? Because the EMF lags behind the main field MMF. So what if I have it here? Then again, this is the resultant MMF. This one is the resultant MMF, and the phasor that represents the EMF because of the resultant MMF is the EMF here, and again it is 90-degree here. So thus again in the same way, this MMF vector load angle representation between the MMF vector can be translated into the angular separation between the field MMF, field EMF, and the resultant EMF here. So thus sometimes we say the angle delta is the angular separation between the MMF vectors, and we can also say angle delta between the EMF vectors here. So it is the same thing here, right? Yeah, this is what I said. In fact, you have the resultant MMF, you have the main field MMF, and this is your armature reaction MMF here. Now, again, when we model the generator, so we model the generator in a more simpler way as a classical model. So this is the source representation, voltage source representation. That will be basically the EMF, which is induced on the generator stator terminal here. Then the generator has reactance. It has the armature resistance, but we can neglect it here. And then this is your generator terminal voltage here at the output generator terminal. And this is the current flow through the stator terminal. So we can write this equation, right? It's very simple case following the Kirchhoff's voltage law here. And now if I consider terminal voltage here as your reference phasor. So this is your terminal voltage, which is a reference phasor. But since generator is inductive in nature, so we said the current lags behind the reference voltage here, right? By power factor angle here. And since this part is neglected, so the drop across the synchronous reactance, it is J times IXS. So this phasor, the voltage drop across the reactance, synchronous reactance, it is 90-degree to this phasor here. So this is 90-degree here. And then the resultant, what you get it is this one. So even in the case of when you talk about the power flow from the generator stator from the induced EMF part to the generator terminal here. Even in that case, you have the angle delta associated here, and this is the, you can say, the angular displacement between the excitation EMF, this one, or the terminal voltage here. So the power flow from the stator, that again depends upon the rotor angle delta here, and this is what we have written it here in general. So it is product of the multiple of the voltage at the two ends, synchronous reactance, and the sign of the angle delta here, right? Yeah. So now with this, if you when we have modeled the SMIB system, we have not considered the damper winding effects, and we have actually, if you refer to the section from the Kundur book, from there we have written this equation. And now when you look at this term, the torque, so thus the change in the torque, the electromagnetic torque, it has two components here, the first part and the second part. First part is because of the change in the angle, and second part is because of the change in the flux linkage here, right? Okay, now that means if you go back here, or maybe I take here, so it means that whenever the magnitude of the current, or thus the armature reaction MMF changes, if this quantity changes, right, or that is this one, if this quantity changes, angle delta will change, right? This is one part. So this angle delta change is because of armature reaction MMF, right? This is one part. Then another part, when I referred, if you I said that if the current, if that means, if let's say the loading of the current increases, if loading of the current increases, it means that I say something here, let's say this one, if you have the increase in the current here, right, that means let's say load on the generator terminal has increased, so this component will increase, and as a result, this component, what you have it here, it will also affected, and this will again change the angle delta. So what you find it here, the angle delta change, right, rotor angle delta change is not only because of the load here, but also because of what you have it here, the armature reaction MMF here. So thus the torque, which you have it here, the torque change which you have it here, it is it will be influenced, the change in the torque will be influenced by two components. One is the component of rotor angle change because of the load, and another is the component due to field flux linkage, of change in the field flux. So because of these two, that means the load angle part and the field flux part, these two results to because of these two factors, it results to change in the electromagnetic torque here, right? Now when we look at this equation, we can say that this, because we have just introduced some constant here, K1 and K2 constant, right? So if the flux is constant, right, if there is no flux, no change in the field flux, right, then in that case K1 will be defined by these two. And if delta is constant, let's say the load is constant, right, you're not changing the load, but you're just changing the field flux, or you are just changing the flux, not changing the field flux, but changing the load, that's where. So thus in that case we have the K2 here. So thus the case constant K1 and K2, they are given by this ratio depending upon which term is constant here. So that was the term which we have discussed earlier. And from SMIB system, we can draw 3 states. And then is in the state space representation, we have 2 input variables. One is the mechanical torque or mechanical turbine power and the field excitation. And if there is no input from the turbine side, no change, I mean, right? If there is no change in the turbine side, it will be 0. And if similarly, if there is no change from the excitation side, this term will be 0. So depending upon if that means the turbine power is kept constant or excitation is kept constant, right? Remember one thing, when I say delta Tm, so that means incremental change in the turbine power or incremental change in the field excitation. Constant, this means it will be 0 here, right? Anything up to this part?
So here, this change in phi is the change in the flux.
Change in the phi is the change in the flux, yeah, field flux. And this field flux will be because of your excitation system, right?
Okay.
This is one part. But
and what
but
is
I will,
T3?
What is?
T3.
T3 will be the actually it is the time constant of the excitation model. I have not discussed so far, but it is in the equation here. Maybe I will, when I discuss as a modeling of excitation system, there it is actually. Yeah, it is a part of the excitation system time constant model. Yeah, it is that way.
And this delta is the angle, right?
This
delta.
one, this is the load angle.
Yeah, load angle. Okay.
Yeah, this is the load angle. No, and this delta is the incremental change, right?
Okay.
This is incremental change, and this is the load angle. Yeah, right. The angle which we have discussed here, it is this one. It is this one term, or maybe what we have it here. It is this one term, right?
Okay.
Okay. But one thing you should understand that even if you do not have a change in the excitation system, let's say the load has changed. Okay. When the load changes, the current will change here. Agreed?
Yeah.
Yeah. Now, when the current changes, then this will change, right? And when this quantity changes, this is armature reaction MMF. This one.
Oh, the EMF. Yeah.
MMF.
Oh, MMF. Okay.
MMF, right? So because this armature reaction MMF is directly proportional to current here. Just see here. MMF means it is a force, and that force which is responsible for the setup of flux, right? Because when you have the flux setup, and that flux is because of force, and that force we call it as MMF, magnetomotive force. And this magnetomotive force is directly proportional to the current here. Higher the current, higher will be the MMF, and thus higher will be the flux, we say. Am I right?
Yeah.
Yeah, because they are related with the term permeability, if you remember. Right?
Yeah, I remember this about AC machines.
So in that case, if we change the current here, if we change the load, this current will change, and thereby MMF will change. So that means the loading on the generator causes this angle to change, and this angle change is not only because of the load, and again it is also somewhere related to armature reaction MMF as well, right? This is one part. So this is what we have here. We have it here. So with that, yeah. So I think we had this block diagram last time, and this was the second order model. And you can see here that there is a 1K constant, which is with delta fed here. And then we have another K constant, K4, which is with the angle delta here. But at the moment we say we are discussing constant field circuit. So that means we are not regulating the excitation system. We keep the fixed voltage excitation here. We are not changing this quantity, right? And so that means the torque here. the electromagnetic torque, what you have it here, it is two components. One is K1 into delta with this part in this loop here. And then another loop is this one, complete loops. It is this one path. So it will be through K4 times del delta into this term, and then this one. So del delta is this one, right? So so if you have a constant field excitation, this one, then the flux variation, this flux variation, what you have it here, this is because of the field circuit here. There is a field circuit, but we are not regulating the excitation voltage basically, right? Because rotor has the field circuit, right? Rotor has the field circuit here, but we are not having any excitation system, because, and we say, let us assume that it is a constant, right? We don't have excitation system. It means the system is excited, the generator is excited, because we assume that the torque is developed, but we are not regulating it. So it means it is constant. This field voltage is maintained constant here, right? And so thus this quantity, what you have it here, it is actually the feedback, because this term which you have it here, it is to the feedback. There's a change in the flux here. The change in the flux which you observe in the rotor circuit, it will be through the feedback from delta through K4 constant here. It is this one. So in fact, I have illustrated another figure here for in terms of phasor. If you refer from the previous phasor representation, this is the main field here, right? And let's say this is your resultant field, and this is because of armature reaction MMF. So this is your armature reaction MMF here. Now let's assume that if there is some change here, some change applied on the generator terminal, right? Let us assume that. Then what will happen? This incremental change of, in fact, incremental or decremental, right? As shown here, it is a decremental. So this is a change here in the angle delta, and thus the curve. So what you have, in fact, this resultant amount factor shifts to this one. It is this way, and then the change in the armature reaction MMF which is applied, it is this part here. So thus the result, what you get it here, it is this phasor representation after the change, and this is the angle delta, and this is your change in the armature reaction MMF here. Now what you observe here in this case, here you have a demagnetizing effect here. What you observe that delta through K4 has a minus sign here, and thus this one, in fact, it results in a demagnetizing effect here, right? So that means the flux in the machine air gap reduce actually, right? It reduce, and thus it will change the angle delta, right? Now this change in the air gap torque, which is because of the change in the flux, right? Because change in the field flux is because of demagnetizing effect here of armature reaction, and this is on the main field. So it is on the main field here, and that will cause the rotor angle to change. So now we are discussing about change in the torque due to change in the angle, right? It is in fact ratio to 2 because of the field flux here, due to the field flux here, right? So we write in this way, because if you refer, this is K4 into delta K3 into K2. So the quantity which you get it here, it is this minus of, because this is the minus sign. So K2, K3, K4, K4.
What about K1? Why is K1 not included here?
Oh, okay. No, that's we are discussing the change in the air gap torque, which was from the angle, but caused because of this one, because of demagnetizing effect. Because of demagnetizing effect, we are discussing here, right? We are not discussing this loop at the moment. At the moment, we are not discussing this loop.
Okay.
Right. At the moment, we are discussing this part here, right? That's why it is written due to this one flux. because this component is here and it involves this loop. Okay, yeah, we will have it later on. We will include this one also later on, but we start from here, right? Okay, so this is what we have
Okay.
written. Yeah. Then we do some manipulation here because this is divided by this term. So because this is Laplace transform, right? So we just want to do some manipulation here. So we got this one, and now what we write in this way. So we have this term. So now you can see this is because when you do the manipulation, so this is S into del delta. So del delta multiplied here, it is this one here, right? Now this term we will write it as this one. So this is actually the synchronizing torque coefficient due to change in the field flux. And now this term, we now you can see here what is S times del delta.
Derivative of the delta.
Derivative of angle or angular speed. So we have this one. So thus from the previous discussion, if you remember, the term which is related to angular speed, we refer it as damping torque coefficient. So this is a damping torque coefficient because of change in the field flux, and this is the synchronizing torque coefficient because of change in the field flux here. So thus from this equation we write down this one. So this is the change in the torque, which is again, now you can see it is it forms two components. One is in phase with angle delta, and another component it is in phase with angular speed here, right? Okay, then so now we can write the synchronizing torque and the damping torque coefficient, let's say at some oscillating frequency, because here we had the angular is this is the Laplace transform S here. So if you want to know what is the torque, synchronizing torque and the damping torque coefficient at a given frequency, oscillating frequency, we can write in this way. It is from the same previous relationship here, in fact, here. So we can just substitute. In fact, I have shown it later on. So you can just substitute what is the angular oscillating frequency here and then solve it. So now, yeah, you talked about why we are not included K1. So it is this one now. If you refer from the previous relationship, torque, it is this one at a constant field excitation. So we did write delta T, del TE, K1 times del delta. So the total torque becomes K1 del delta and these two terms here, which were, so, and now these two, what you have it here, because from the previous relationship, because here this one, they are with S term here. So thus the synchronizing torque coefficient due to the field, due to change in the field, damping torque coefficient due to change in the field, they depend upon oscillating frequency. But at a constant field flux K1, this is just constant value. So they are not dependent on oscillating frequency. So this is your total torque now. And now those components which are function of delta. So we can write in this way. So this becomes net synchronizing torque coefficient. So net synchronizing torque coefficient, because K1 is a function of del delta, this term is also a function of del delta. So this is your net synchronizing torque coefficient here, right? So now we have taken into account.
That makes sense.
Yeah, then we have taken into account what is the, but again, we are saying, we are not saying total, because when we say the word total, it is sum, right? But because when we take some example, we are saying net. So maybe this term is more or this term and so on. So there will be some algebraic sum here, algebraic. So that's why we're saying net synchronizing torque. Then damping torque from here. This damping torque, remember one thing, this damping torque is because of the change in the field flux only. Yeah. Armature reaction field flux, right? This is not because of the load damping constant, right? And thus that means there is some damping torque. There is some damping torque provided in the machine because of change in the field flux as well, and that is due to change in the angle. Because when the angle changes, when you look at here, when the angle changes, when this angle changes, the field flux will change, right? This will change. Armature reaction MMF will change, and that will cause synchronizing torque coefficient to change, and as well as damping torque coefficient to change here. So thus, depending what you find it here, this is the synchronizing torque coefficient, and this is your damping torque coefficient here. Yeah. Then we have some case here, case study. So we are talking about studying what is the effect of change in the field flux on system stability here, right? And the first case we consider steady state condition. So let's say that there is no perturbation, no disturbance, the system is standstill, right? So it means that there is no oscillating frequency associated in the system response. So it means that Laplace S and that we are seeing a low frequency oscillating frequency, right? And J omega stands to 0 here. So that means if you refer from the previous relay lesson, what we had it here, this one, in fact, or I have written down here again one more time. Yeah, this one. So from the previous relationship, what we have it for torque at oscillating frequency. So this is S is equal to 0, right? So this term cancel, this is 0. Then again, this entire part is 0. So at the steady state, omega is 0. So that's what you get here, the torque. The change in the torque due to field flux, it is only given by this term. That is at steady state quantity, steady state condition, basically. So from this relationship, we can know at a steady state condition, we can know what is the change in the torque due to field flux. So it is given by this relationship here. Right? It's very simple. We have just substituted the value of S to be 0 here, nothing else. So from here, what you find, what you observe here, the torque, the change in the torque due to field flux, due to change in the field flux, right? It has a negative synchronizing torque component. So that means, let's say system is steady state, there is no load change, right? There is no change on the load side. But let's say you change the, if there is some change in the field flux, right? Or if there is some change in the field flux, then it will have a negative synchronizing torque coefficient here, no negative synchronizing torque component here. This is what it reflects here. But again, what will be the net synchronizing torque? So net synchronizing torque is this one. And that way, now here you can see. So at steady state condition, the net synchronizing torque is K1 minus this term. And this quantity is usually positive. So it will be the difference of the two term here. Different. What is the K1 value and what is this term? So thus this term can be positive depending upon what is the magnitude of this with respect to this one, right? And from the previous, in fact, block diagram, what we have it here, it is this term and then this loop here. So it means that the air gap torque, what we have written in this way. So the air gap torque, it is the change in the torque due to the field flux plus K1 delta, what you have it here. So it is this one. So the change, the net torque, net change in the air gap torque will be depending upon the storm, and system can become unstable if this quantity is more than this quantity, and steady state limit can be defined when the two are equal. The two terms are equal, the K1 equal to the product of these three constants here. So that is the steady state stability limit here, right? And if this term is greater than K1, then the response would become unstable here, right? Because in that case, it will be equal to minus of some time delta. So it means the torque the air gap torque is negative basically. So the system response will be unstable in that case. But this is the case we have steady state condition, right? Anything on this side? Yes, please.
No, it's okay. It's
Okay.
clear now.
Okay. So then, if you took the if you take the second case here, oscillating frequency. Now, from the previous relationship, if you recall, we had this term, and then with constant field, so we had this term, and from the previous case, we had this one here. So it is something, in fact, this way. So we can just manipulate. So we might multiply it here, right? And then we have written down this equation. So that was our function of synchronizing torque and the damping torque due to change in the field flux here. So now we want to analyze the what is the effect of field flux linkage on system stability at a given oscillating frequency here. So we say S is equal to J omega. So if you remember for the previous relationship, it was this one, because we had manipulated and then we had this term. So it is this equation here, right? So if you want to compute what is the torque at oscillating frequency, you can do that. So we just take this relationship, and the net synchronizing torque coefficient will be given by this one. The net damping torque will be given by this one. And let's say that you want to understand what is the torque, air gap torque for a oscillating frequency. Yeah. So let's say this is the eigenvalue. Let's say you want to have it for low damp mode, right? And which corresponds to some 1.42 hertz or 0.75 hertz oscillating frequency. So let's say this is the corresponding eigenvalue. So what we have it here, if I consider that this real part is small, much smaller, right? Because I consider it is the dominant oscillating frequency, right? So dominant oscillating frequency means, what do they mean by dominant oscillating frequency?
You mean the
Yeah.
frequency of the power system, the 50 hertz?
No, I'm talking about low frequency oscillation.
Oh, it means it's a local one, right? The local area oscillation.
Yeah, local area oscillation. But when I say dominant oscillating frequency, it means that its real component, right? Its real component is nearest to the imaginary axis, nearest. There will be several eigenvalues, right? There will be several eigenvalues, yeah, right? There will be several of them, right? There will be several number of eigenvalues here, right? There are several of them. But which eigenvalue is dominant? The eigenvalue is dominant whose real part is the smallest one. So I will say it is this one. This eigenvalue is dominant because its real part is smallest. Because if I take this one, its eigenvalue real part is this one, or if it is somewhere here. It is somewhere here for this, or somewhere here for this for this one, it is somewhere here, or for this one, it is somewhere here. So now this, the real part, they are more than this one here, right? Numerical value. So those eigenvalues which are nearest, because this is imaginary axis, so they are nearest to the imaginary axis, so thus they will be the dominant one. And thus let's say that for a small value of a dominant eigenvalue, right? So let us assume then this quantity S is equal to J omega. Then we can solve. We can solve what is the synchronizing torque coefficient and damping from this quantity. We can solve this part. We can substitute S is equal to J omega term here. We can solve this. Similarly, we can solve this part, the damping torque coefficient, this one with this one. So thus, and what is omega naught? That will be rated angular speed. So it will be 314 radian per second or 377 radian per second here, right? So we can solve this too, and then we can compute the value of Ks and Kd. But again, it is due to change in the field flux. due to armature reaction here. Right, up to this point is clear, I think.
Yeah.
Okay, then we take the case where you include now excitation system. So what do we have it here? Excitation system and AVR. So this is the excitation system representation by a transfer function, and then AVR part here. So this is the complete AVR and excitation system part. So you can see here that you have a sensor here, voltage transducer, and which will have the change in the voltage, generator terminal voltage here, right? And that will be given by K5 times del delta and K6 times del psi D here. So it is this one. So just the terminal voltage error, the change in the generator terminal voltage error, it is this quantity here. So now when we have included AVR, this one, as you can see here, this term, we can write it as this multiplied by this one. So 1 by 1 plus STR, right? It is this one, 1 plus STR multiplied by del ET basically, or it will be in these two terms. So you have it this way. So this is actually the term, what we call it, del ET, yeah, this one. Then if I consider the reference voltage here, 0, so that means it is constant here. All right, we didn't have any reference voltage here, constant, no change. Then now let us understand what will be the change in the field flux when you have AVR and the armature reaction included. So this is the change. So because if you look at here, this one. So this is the change in the field flux when you have AVR here. This is the AVR plus the change in the field flux due to K4 feedback here. And because this one, this is what we have discussed earlier, change in the field flux due to armature reaction here. So it was from here, it was from here, and then with the AVR, when you look at, so because this is some additional term which is added here, so we will discuss that part with inclusion of these two terms here, because now you have del EFD, because earlier del EFD was 0, but now del EFD will be some quantity here, it will be some quantity here. So as such, we have this one. So you can see K3, in fact, K3, 1 plus ST3 multiplied by this term, and then again del EFD here, right? So what we find it here, GEX times del V1, because this we have kept 0, so G is GEX times del V1 equal to this quantity, and then another term is K4 into del delta. So another one K4 del delta. So that is del psi FD. And now we here we will substitute this one from here, and then we will do some manipulation and then rearrange. So finally we get this one, right? In fact, we have substituted this here, and then because this is 1 plus ST3, so you multiply by numerator and denominator by 1 minus ST3. So when you solve it, so you get this now. So this is actually now change in the field flux with both AVR and armature reaction reactor. So this is now. So from the previous relationship, we had this top. So this was given by this one, K1 into del delta, and now we have this term. So this term, we have it here, right? So you just multiply by K2, right? You multiply by K2, and then you get this one, and then plus K1 into del delta. So what is the torque here, right? So the change in the torque, Now we are seeing change in the torque due to AVR plus armature reaction with this part. So that will be equal to K2 times del psi FD. Here, this is the part here we have written here. So we have just multiplied K2 here in this term. And so this is the term. And then finally we can obtain what is net torque. So then again we can solve two cases. So one here steady state. So we can substitute S is equal to J omega to 0. So when you refer from the previous relationship here, this one, we have S term here, we have S term here, this one, and we have S term here. So it means this becomes 0, this term becomes 0, this term becomes 0. So finally you get the torque, change in the torque due to AVR plus AR is this one. And now this is your synchronizing torque coefficient with AVR plus AR. So this is different now. Earlier we didn't had excitation system, so and we had the synchronizing torque coefficient because of AR only. But now when you have excitation system, so it is this term, which is actually the synchronizing torque coefficient with AVR and AR. Then we can write what is the net synchronizing torque coefficient in this way, because we have the K1 into del delta. So this is the net synchronizing torque coefficient now, right? This is just the modification we are discussing actually. And if you want to compute what is the change in the field flux at synchronizing at oscillating frequency here, right? Then from the same relationship which we had it here, this one, you just substitute what is S is equal to J omega. So we substitute it here in this term, it is the same equation, and then we get this one, right? Anything on this part? Yes, please.
It's okay.
So in that case, now you can calculate what is the torque with both AVR and AR. So in fact, when you solve it, when you solve, let's say if you have some numerical value and when you solve this quantity here, right? When you solve them, when you substitute the values here, then you get this one. And in fact, you will get some numerical value for which will be a function of del delta, and you will get some numerical value which will be a function of this term. So it is J times del delta. So with the previous analogy, because the component which is a function of del delta and the component which is J del delta, it is actually damping torque. And the function, the quantity which is in phase with del delta, it is synchronizing torque coefficient. So thus here it gives you synchronizing torque coefficient, and this gives you damping torque coefficient here. So we can solve, we can get what is the value here, right? And from the previous block diagram, what we had it here. So you can see there is one more additional state being added because you have 1 by S term here. So it means when you obtain the state space model, so we have one more state. So this is 4th row and 4th column being created. So it is now 4 by 4 matrix here. Now, in general, what we understand that AVR, what is the effect of AVR? It is basically governed by what is the model of excitation system and what is the value of K5 here, right? That is basically what we observe. And if we have K5 less than 0, that means negative, then AVR may have positive a synchronizing torque coefficient here. It may have positive if K5 is negative. So we had this example, and here you can see that we are analyzing the effect of different gain values in the excitation system for the AVR. So we have some value of K1, K2, K3 here, K4, and for K5 you see here it is it is negative here, and we have considered excitation system by a simple gain. So the previous relationship what we had earlier, in fact, I mean this one, because this is the with excitation system and AVR at a steady state. This is the one. So at a steady state, you get this quantity, delta change in the torque due to AVR and AR. So it is this one. So now with use of this relationship, we have it here, this one. So what is at a steady state? So what is the steady state synchronizing torque coefficient from the previous relationship? So here we have substituted GS is equal to K. So then substituting all these values, we get this one here, right? Now this is steady state damping torque coefficient, right? And here you can see, if I say what is the value of K again here, right? So it could be 0, so then it will be completely 0 in fact. But if I say 10, 15, 20, so this torque will change, right? So what we observe that normally influence of AVR is to increase the synchronizing torque component here at a steady state value, at a steady state condition. But the same analysis when we perform, let's say, oscillating frequency of 10 radian per second. So we say, let's say j omega is equal to 10 here. And then we have considered different magnitude of gain here. We have varied it here. And now this column, what you have, it is this one. So this is actually the synchronizing torque coefficient due to change in the flux because of presence of AVR and AR. And this is net synchronizing torque coefficient, and this is the damping torque coefficient here. Right, these two, what we have it, in fact, this one and this one columns, we have calculated from here. In fact, we have calculated from here. As I said, this one oscillating frequency is substitute j is omega is equal to 10 here, right? And you solve this the components, you solve this part. When you solve it, substitute different value of gain here, and then you will get something here. It will be like K times del delta and L times j omega delta. So it will be this part and it will be this part, what we have it here, this column and in this column. This column is basically the net synchronizing torque when we have the K1 added here, that's all. Right? Now I think this table must be clear to you how we have solved it, and then
yeah, it's more clear. Yes.
Anything about Andres? Andres, any comment?
Not really.
Okay. So next, now we move to, yeah. So what we finally understand from the swing equation, this was the term, and now we have written it here, del T. So in fact, remember one thing, this is the synchronizing torque factor, we call it as. Maybe in some book they have different terminology, but they call it as synchronizing torque factor. This is damping torque factor, and thus it is given by this way. So Ks times del delta or Kd times del omega. And I think I have discussed that if you have a constant field, then both are positive, then you may have a stable response. But if there is a negative TS, then you may have this we call it at non-oscillatory instability. Remember, this oscillatory is instability, and this one, it is little bit different. This form of the response and this form of the response, it is different here. This we call it as oscillatory instability, and this, because this is in oscillation at a certain frequency. So that's why it is referred as oscillatory instability. But if when you have this form of the angle deviation, it will not be at a given frequency, oscillating frequency, and that's why we call it as non-oscillatory instability. And this we experience when we have negative synchronizing torque coefficient. And so with a constant field voltage, when we have, that means no regulation of field field circuit, then KD is always greater than 0. And in some cases, KS, because KS will be the synchronizing torque component from the network side and plus the machine side. So that will be due to the change in the flux from AVR area. So this can be less than 0. So that means with constant field voltage operation on the generator, synchronizing torque coefficient can be negative in some cases. And you may observe this kind of instability response here. But if you have exciter included, if you have exciter regulation, then synchronizing torque coefficient is positive. Just say, because what we have, the resultant is this one, and this is K1 plus this sum, and thus it will be more or less as you look at here. The net synchronizing torque coefficient, when you look at it, is always more or less positive here, right? That is one part. So thus it is always positive. But this one, the damping torque, when you look at here, the damping torque coefficient, what you find it here? For certain gains, it is okay, positive, but for other range of gain, they are negative. So it means that sometimes the damping torque coefficient, which will be basically again the sum of, because we have not included the damping torque coefficient from the generator and the load side actually, and then the sum of these two, they can be negative here. But again, but it can be possible that the load damping constant and this this term damping constant, low damping torque because of field flux variation, they get balance. If they get balance, then it can be in some way positive here. That is possible, and thus Ks is positive, and thus this term is also positive. So thus you may have a stable response. That is possible, and that's why we say that there has to be load damping constant, which will take into account if there is a negative effect from here. So it will compensate that part. And if it is not, then you can see here that with excitation control, TS is always positive. TS is always positive, but TD can be negative. That means KD here, it can be negative here. But here it is positive, but here it can be negative. That is the difference you also here. Right. So thus now we want to have the how to improve the response, right? How to improve the response. So do you want to have a break for a few minutes before, because this will be a new topic?
Yeah. Yes,
okay.
please.
Okay, for 3 minutes.
Okay.
Fine. Okay. Okay. So we discuss the some analysis on the SMIB system, and that was understanding how does the excitation system, and then again finally taking one example, how does the gain of excitation system will what will be the impact, what will be its impact on the synchronizing torque coefficient and then damping torque coefficient here. And so this, it is possible that what we understand, in some case you may have positive, you may have negative coefficient, and thus the response can be stable or unstable. But it is important that to have system stable for all the operating conditions. And for that, we design the stabilizer, and we have a controller basically, and we have named it as based on its what is its objective. So this controller is meant to stabilize the rotor angle oscillation. So it provides a damping effect. So it improves the damping effect. That means it enhances the damping of the rotor angle response. And thus it tries to damp out the rotor angle oscillations if there is some. So thus, as I said, is the controller. And so the main function of the stabilizer, that is the controller, is to damp out, to improve the damping ratio better basically. So because if you have some rotor angle oscillations, this is a well damped response, because what you find here that the amplitude of oscillation is decaying down, and thus the angle will settle down finally. But if you have this response, this is definitely non-oscillating instability, and thus the response goes. What you find here that in this case the rotor angle is just keep on increasing actually. And if I take this one, oscillating instability, in this case you find the response goes on increasing. We don't want this kind of response basically. We want the damp out. We want the, if let's say there is some disturbance took place, okay, fine. So rotor angle will oscillate, let's say for how many swing, one swing, this is one swing, this is two swing, right? And then maybe one more swing, and then finally it will settle down. So we want a good damping ratio if there is some rotor angle oscillations following any disturbance. And to achieve that, we have this controller. Now, and again, from the previous discussion, we understand that the synchronizing torque coefficient and then damping torque coefficient, both are function. Both depends upon how does the field flux, changes, right? So here you can see the field flux depending upon AVR and armature reaction. And again, in this case also damping torque coefficient, which is a function of field flux due to the presence of AVR and AR. So that means the synchronizing torque coefficient and the damping torque coefficient, they are somehow related to how does the field flux vary, how does the field flux linkage takes place in the generator, in the air gap, right? And thus, so that means it is somehow related to excitation only. So thus it is this controller, power system stabilizer, it will, how it will improve the damping. So that means it will add, it will feed some additional signal. It will improve the damping by injecting an additional signal through the excitation system, right? And so it means it will be acting towards improvement in the damping of the rotor angle oscillations by providing some excitation signal here to the exciter system. So that means, what if you have it here, when you look at, this is your exciter. We have represented it by a gain. Yeah, this is the field voltage, right? It is the same relationship. In fact, when you look at, this is a reference voltage, and this is your V1. If you look at the previous block diagram, when I here, reference voltage, excitation system here, and V1 here. So this V1, what you have it here from transducer. So that means the stabilizer will have a additional signal, or sorry, I go back, auxiliary signal fed to the excitation system. So here, so this is the stabilizing signal on an auxiliary. Sometimes we also say auxiliary signal or a control signal being fed to AVR of excitation system. So this is exciter, reference voltage, and from the this is generator terminal voltage error to the transducer here. And this is the control signal, stabilizing signal, which we obtained from the power system stabilizer. So this is the block diagram for power system stabilizer, whose output will feed additional signal. It will feed a supplementary signal to the excitation system to improve the damping for the rotor angle oscillations. So what you observe here, if we want to, this is the controller basically, this is the stabilizer, and this is the output here, and again you can see it is the voltage signal here. So that means the coefficient, the synchronizing torque coefficient and the damping torque coefficient, they were influenced by field excitation, field voltage, and thus the stabilizer also provides a signal which is a voltage signal. So the variable, the control variable, it is actually a voltage signal fed to the excitation system here. So again, it is a voltage signal here, right? But if you look at the system representation here, so what you find here, this is the output quantity, and this is the input quantity. So that's the feedback. That's the feedback to the stabilizer design. It is actually angular speed, right? It is the angular speed here. This is the input, and this is the output here. So this is the voltage signal. So if now if you want to have the transfer function representation for the stabilizer, which will provide, you can say, some improvement in the torque, yeah, right? That is what. But here we have it is through the direct feedback from omega here, angular speed, and thus it is expected that the setting of the power system stabilizer is in such a way that it provides a positive damping torque here to the generator, in fact. So what you have it here, there are three stages in the stabilizer design. There are three blocks here. The first one is the gain, basically, and that is the stabilizer gain here, this one. So that provides how much should be the damping, what should be the amount of damping ratio to be improved or enhanced by the power system stabilizer here. Then again, here we have some filter, washout filter. So it could be like something, what you have it here as a high pass filter with a washout time constant TW, which will be in the range of 1 to 20 seconds something here. So as to allow only those signals. All right, it should allow only those signals which are with the oscillating frequency of omega r here. So that we don't want to, because if there is some rotor angle oscillation, all right, so that characteristic rotor angle oscillation as a given frequency, it should not be changed. So that signal has to pass through this filter here, and that's why we have this one. And then we have a compensator bank, compensation part here, and we have both. This could be the lead compensation, and this is the lag compensation. Maybe I think in your advanced course, advanced control course, you will study about the compensators here. So we have use of both phase lead as well as phase lag. So the numerator part provides you phase lead, and the denominator part provides you phase lag here. So we can have phase lead compensation for whatever the frequency range we want, because we want to improve the damping ratio for an oscillating frequency of this much. So that means if this dial omega, it is in oscillation. Now again, remember, we talk about the rotor angle oscillations, right? We talk about the rotor angle, but the rotor angle is related to dial omega, angular speed, right? So in many of the cases, we use dial omega, Can anybody say why? Yeah.
I'm not sure actually. I don't know.
Normally, just see, this is angular speed, right? And this angular speed can be measured easily. But when I talk about the angle, can we get it? Can we get the angle estimated from the machine internal part, rotor angle?
No, usually you measure the speed and then you
we can convert into
integrate
delta.
it.
Yeah. So that is normally we do, because the measurement point of view, angular speed is much more convenient in use as a feedback signal rather than rotor angle, because we have to introduce some sensor and then get it. But nowadays, let me tell you, PMOs, right? So the PMOs provide the phasors, and it is the voltage phasor. So this is another way. Thus, the rotor angle is not exactly the rotor angle, but it is the voltage angle. So that is another option which is available now, which can be used as a feedback. But still, again, it depends upon how we utilize it. Perhaps nowadays it is available. So thus here we have the, depending upon what is the frequency range of interest. So this frequency range means low frequency range. So because the rotor angle will be oscillating either in the inter-area mode or the local mode of oscillation. So it is in this range here. So we want only those signals to be here. In some cases, we may have the more stages in the compensation stabilizer design, but this is a single stage, yeah. But we can have 2 stage of compensation as well, yeah. Right. And then, yeah, this is the one which I discussed. And now when we integrate this stabilizer part over here, so we have this one here. So this is the complete SMIB system. We had it, and now you can see this representation, this block representation, what you have it here, it is from the power source and stabilizer. In fact, it is this one. I mean, it is this one. Because when you look at input to stabilizer is dial omega. So you get it from here. Yeah, you get it from here, dial omega. It is fed back. And then output of stabilizer, it is this one. So its output, what to feed it here? It is this one. So it is in the AVR section. So this is your AVR block. So it is fed here. So this is the complete SMIB system with exciter, AVR, and PSS, all, everything completed, included here now. So this is now complete representation of SMIB here, right? The classical model of generator, then you have a field circuit, then you have AVR part, and then you have stabilizer part also here. So in fact, if you mostly the generators and the exciters which we have, right? Because if you look at here, we have represented the exciter by a gain here, right? So this the transfer function for exciter we have considered as a simple gain, but we have more detailed model of excitation system basically. And it could be as a first order model also, right? So or there could be more detailed model of excitation system. Then again, the generator representation could be as something the field circuit part. When you look at here, this is the field circuit part. So what you have it here, in the field circuit part, it is, let's say, some constant here. This is K3 divided by 1 plus ST3. What does this mean? If you have it representation of this field circuit in this form, what does this mean? That is
it's like
in terms
a low
of
pass filter.
yeah, but what is the response? I mean, can you say something? Because normally, if you represent a system as of this form, and if you maybe in the advanced control you refer, let's say this is 1.0, right? If you apply some unit step signal, you apply a unit step signal here, right? Unit step signal. So what will be, you have applied some unit step here. What will be the change here? You will get it. What will be the output response?
It will be like a first order response.
So first order response is always this way.
Underdamped, yes, always
It is under,
underdamped.
it is under down. In fact, or maybe this one, it will be, or maybe it will be something this. So that means the
Yeah,
response is lagging. So the
yeah,
response of a first order system is always lagging, right? So same way, the excitation system, if it is a first order, so its response will always be lagging. Okay. So most of the normally you have the generators, and then you have excitation systems. They always have phase lag characteristic, and thus their representation is always in this form. So 1 by something t. T is the time constant of the this system here. It could be for generator, it could be for a excitation system also, in the simplest form. So in that case, when you have the I'm not sure if you have studied the Bode plot.
yeah. We
Okay,
have.
okay. So thus there we draw the magnitude versus frequency, and then the phase angle versus frequency, and thus the because it means that generator and exciter, they always have phase lag, right? That means for a given range of frequency, for a given range of the frequency, because we are considering low frequency, yeah, right? For a given range of frequency, which is of our interest to improve the damping, so exciter and the generator, there will always represent a lagging effect, right? Then in that case, if you want to improve the damping, the compensator, the PSS should provide a leading effect, leading compensation, leading phase effect. Am I right? So, but again, in some cases, we may also have leading compensation as well, right? Leading compensation effect from the system response side. So in that case, the compensator should provide a lagging phase effect. So thus, in a generalized way, the phase compensation which we design for PSS, it is always with the lead compensation part and with the lag compensation part, because sometimes we may have both actually requirements depending upon the system response. So, but how much? But again, we cannot have full compensation. But as you can see here that this is T1. If we say T1 is the position of the poles here, right? This is the pole. Sorry, this is the position. This will correspond to the position of 0, and this will correspond to the position of a pole. So, and what you find here that the magnitude, if I say this one, so in that case, it will be like a lead compensation provided here. So as such, we have both lead and lag compensation, because we cannot have full compensation here. So thus it represents what is the range of frequency here, frequency interest here, and thus to provide the phase compensation. Yeah. We have one example here from the Kundur book in 12.4, and I request you all to go through that. Right, I will have some discussion here, because they start with the first case here, and when they have a second B part with the PSS included, and then all this is the operating condition. So the first part, they have it, this is the state matrix, and when they have both AVR and the PSS, so all the states are here. Now we have discussed up to 4 states, right? And when you refer to PSS inclusion, we have one state here, this one, and another state here. So thus altogether that we have 3 and 6 states in the A matrix here. So it becomes a 6 by 6 matrix now. And with these values, they have obtained what is the eigenvalues and then participation factor. And the second part with PSS included, all that part here they have given. So here I have some discussion with the space matrix. So if you can refer to this page. with the AVR. So thus this row, the last two rows and the last two columns, they are not here with when we consider without PSS. So this is the matrix which we have it only with the AVR. So it becomes now 4x4 matrix here. This is the 4x4 matrix with 4 states here, this one. And what you find it here from the eigenvalues here, we have two complex eigenvalues and two real eigenvalues. And omega d damping frequency, and then what is the ratio here. So what you find it here, this one, the eigenvalue is positive. So that means the location of eigenvalues is on the which side? Right hand side of the plane, yeah. And thus with AVR included, the response is unstable because the eigenvalue is placed on the right hand side. And what you find it here, it is at this is 7.23. This is omega. You can convert into hertz here. So it is oscillating at 1.15 hertz here, right? And when you obtain the participation factor, if you remember, I have said that along the you go row wise, it will be the state variable, and when you go to the column wise, it will be the eigenvalues. And what you find here that generative state variable, this one, because generative state variable is omega and delta here, right? And this is the field flux, and this one is from the AVR side. So these are basically what you find it here. They are lambda 3, lambda 4, this one. So the participation factor of these state variables, right? The participation factor of these state variables for eigenvalues, this one, they are much high. And so that means these state variables, they are not associated with any mode of oscillation. So that means this is that if you look at the time domain response, these are the state variables. So if you look at the time domain response, they will not have any oscillatory response. But if you look at the generated state variables here, this one. So if you look at generated state variables, and they are associated with the complex eigenvalues, right? And that's because the magnitude, when you look at magnitude of participation factor here, for these two state variables, corresponding to this one, they are very high. Because if you look at the participation factor here, it corresponds to this state variable, or if you look at this one, it corresponds to it. So that means these two state variables, for these eigenvalues, their participation is very, very small. And thus, for the complex eigenvalues, they don't, because that means they are not associated with any oscillating frequency, basically. So it is the generative state variable, they are actually associated with the oscillating frequency. And do you observe one more point here? Can you observe something here? In terms of the participation factor value.
They're all positive. That's one thing. But
yeah, yes, they are positive. But when you look at the participation factor of omega and delta, they are same.
yeah,
They are same, because they are just related by integral, right? They are just related by. So that means if you understand the dynamics of generator behavior using omega signal or delta signal, it will be the same. It will be the same, because both both state variable, they represent, they give you same information here in terms of participation factor for a given mode. So that's either of the state variable could be used here. And then when you include PSS, right? When you include PSS, then this is the complete matrix. And now we have these two state variables. That means this row and then these two columns here. And then when you look at here, there are two modes. They are non-oscillatory. Then lambda 2 and lambda 3 and 5 and 6, they are complex eigenvalues here. And when you look at what is their oscillating frequency value, so one is 0.15 damping ratio, another is 0.84. And you can see at all the eigenvalues, they are placed on the left hand side. So with the use of PSS, response is stable, that one. But you find that there are two oscillatory modes. In the previous case, there was only one oscillatory mode here, right? But now you have two oscillatory modes here. One is corresponding to this frequency, another corresponding to this frequency. But here the damping ratio is very high, right? It is very high. And even in this case, it is 0.15, so it is 15%. So it is still good enough. It is still good enough here. So, but the response, because of the control signals and then the system, what you have it here, you have two more additional oscillatory modes here actually. So, but anyhow, the response is stable. System is stable, and then again, good damping ratio, find it here. And when you obtain the participation factor here, you go this way, these are the state variables. You go this way, these are the eigenvalues. What do you find it here? These are state variables. Now look, because lambda 2 and lambda 3, these were complex eigenvalues, this one, right? And they have higher participation factor here. They have higher. And it is this one. Yeah. So that means, because this is, you can see it is a low damp, comparatively low damp with this one, this oscillatory mode. Because this is 0.84 and this one is 0.15. So this is 0.15. Because when you look at 5 and 6, lambda 5 and 6 here, so there is participation factor is much lower. So that means the generated state variables, they have higher participation factor to low damp oscillatory mode, because this is low damp oscillatory mode here, right? And again, you find it that in fact it is 0.528 and then here 0.52. No, I think it should be same actually. Here also it should be 0.528, right? Because let's just say lambda 2 and lambda 3, these are conjugate, right? So it should be same here. So it should be 0.528. Yeah, it should be 0.528. It should be same value, right? And another point, when you look at this one, what does this mean? Is it lambda 5 and lambda 6? This one, which has much higher damping ratio, which has higher damp. Though you can see that they have somewhat higher frequency. They have somewhat higher oscillator frequency, and but good damping ratio, and you can see the participation factor for these state variables and corresponding to these modes, right? This one, they are associated. So that means these are actually the control variables, right? These are the control variables which are associated with this mode, and but they have good damping ratio. So you are not concerned about those mode. You are not concerned about those mode which has higher damping ratio. You have to consider your controller design for those mode which have poorer damping ratio. Although in this case it is 0.15, but let's say it has been something 0.05. So it is just 5%. So in that case, you have to consider some way of PSS design to damp out the oscillation which we observe in this state variable here, right? Okay, anything more? And again, you can see that you can look, if you look at the matrix, you can see that some of the state variables here, right? Because lambda 4, it is actually non-oscillatory, and it may have high participation factor to this state variable, but it does not matter because this is non-oscillatory eigenmode. So we are not concerned with that. We are concerned only those modes which are oscillative. That means those complex eigenvalues. These are the complex eigenvalues. And again, among the complex eigenvalues, we are concerned those modes those eigenvalues which have comparatively lower or the lowest damping ratio. We are concerned with those eigenvalues basically, right? So here they have done some analysis and they have considered what are the values. With the constant field excitation, you can see damping ratio. And then you can see here that with the constant field excitation, damping ratio is poor. But when you include AVR, response damping ratio becomes negative. And again, when you have negative damping ratio, you can see the load damping constant that is negative here. But when you include both AVR and PSS for the same mode, near about, if it is damping ratio of 0.15 and synchronizing torque coefficient and the damping torque coefficient, both are positive here. Right? Anything up to this one? So
that makes sense. So the controller improves the
response.
damping ratio response.
This is what we want from the stabilizer design basically.
Yeah.
Anything more? Or I think you are only two people, but I want you to discuss what should be the deadline. Maybe tomorrow we should fix it because still.
I don't mind. We actually solved the assignment.
Andres, what you say? When should we have it?
Yeah,
Should I keep it
also.
27? Should I please fix it 27?
27 is good, yeah.
Okay, fine. I will announce it here. Okay, fine. Okay. Okay then. So I stop the